Welcome to my presentation at the 23rd GTT users meeting. When I started working for GTT-Technologies in 2016, I wanted to introduce the open system feature to students by simulating the evaporation of the acetic acid from vinegar in the salad bowl. Well, I failed then, and I want to show you now that you can do this much easier today in FACTSAGE 8.1 using constrained Gibbs energy minimization. I will quickly explain the problem. I will show you what happens if you do this calculation without thinking too much about it. Then I will have a short excursus on the history and science of baking powder. I will then go to a second experiment and further application of the virtual system components. Okay, if I read what it says on my bottle of vinegar, I read that the vinegar contains 5.4% of acid. And also when I Googled, I've seen that most vinegars have a pH value around 2.4. Now, I tried to simulate this using Equilib. So I input 5.4% of acetic acid and water. I just select ignorantly all of the species as possible products, and I calculate the system at 25 degrees. This is the output I get. The output table is already a little bit reduced to show only the most important species. First of all, I can see that I have an activity of my acetic acid of 10 to the minus 16 atmospheres. So that's the partial pressure. And if I smell on the bottle of vinegar, it smells like the partial pressure should be higher than 10 to the minus 16. Then I see that I have a concentration of CH4 and CO2 in the aqueous solution, which are much, much larger than the concentration of my acetic acid. And finally, I noted that I have graphite formation. I've never seen graphite precipitates in my bottle of vinegar, so that doesn't make a lot of sense. So what do we do if we see graphite formation in the iron-carbon phase diagram while we want to see the cementite? Well, we just deselect the graphite from the list of possible products. And I've done the same here. And the result I get with this species selection is shown here, and is not that much better. I see now the formation of CH4 and CO2 in the gas phase, and also the formation of especially CO2 or dissolution of CO2 in the aqueous solution. Note that the carbonate acid residue is also part of the system, but just not shown here for brevity. And the pH value also doesn't make a lot of sense if you compare it to the Google result. How do you do this calculation then in FACTSAGE? Well, the first solution is to change the species selection and to be more drastic than I have been earlier when I just deselected the graphite. So now I deselect any species but the acetic acid. So in the gas phase, I only have the acetic acid selected, and in the aqueous solution, I only have the acetic acid, the acid residue, and the H plus selected. And if I perform a calculation now, I see that I have fugacity in the range of 10 to the minus 3 atmospheres, which makes sense. And I have a pH value of 2.4, which also makes sense and which matches the number that you find when you Google. Perfect. What have we done in terms of the stoichiometry metrics? I want to introduce this concept now because it's quite handy to understand it. The stoichiometry metrics combines the information on the species in the phases and the system components. The system components we have in this system are hydrogen, carbon, oxygen, and the aqueous phase electron. For example, the CH4 species has 1 carbon atom in it and 4 hydrogen atoms. What I've done is I have just removed everything but water and the acetic acid and the H+. And by that, I directly link the molar amount of the acetic acid components, the sum of them, to be equal to 1/2 of the molar amount of carbon in the system, because there's no other species where the carbon may go but to the acetic acid. And that's fine. Okay, another way to do this that is available since FactSage 8.1 is the use of virtual system components. For that, we first have to change the input amount from grams to mole, and you can do this after a right click on the quantity field here, and then select convert this reactant amount to mole. And then we add the virtual system component QA, which has a mass of 0, a molar mass of 0, and therefore we need to have the input in moles rather than grams to avoid a division by 0 error. We add this as a second species, and we also add another species, which is the acid residue of the acetic acid. The amount of this one is equal to 0, so we have 0 moles of CH3CO QA-. Why do we need to do this? Because there is a change in the backend of the database that we will see in a second. So if I now go to the menu screen of Ecflip and I right click on the gas and the aqueous solution phase, I notice that automatically these species in red have been generated. And these are the acetic acid with the QA and also the acetic acid QA-, so the acetic acid residue with a QA. And we will now select these species and will unselect the original acetic acid species. If we perform the calculation, we get a result that is again very reasonable. We have a right partial pressure of the acetic acid, and we have the right pH value. Perfect. What have we done in terms of these stoichiometry metrics? Well, we have introduced a new system component. So we need a new column in the stoichiometry metrics. The system component is only associated to the 3 species that are related to the acetic acid. And now the sum of these acetic acid species must be equal to the must be equal to the amount of QA we enter in the system. And that is exactly what we wanted to have, right? Okay, now let us go to a short excursus on the history and science of baking powder. So baking powder consists of mainly 3 ingredients. We have a bicarbonate usually, we have a weak acid, and we have a buffer like cornstarch, which is also used in the baking powder I have here. And the invention of baking powder was pioneered by Alfred Bird in the UK, who in 1843 has introduced sodium bicarbonate in the bread baking. And then the sodium bicarbonate would decompose and would release CO2 during the baking process, which is then needed as a leavening agent. And then Justus Liebig at Gießen University and even Norton Horsford at Harvard University, they have refined this by adding a weak acid like this disodium paraphosphate. And that is then shifting the pH value from the basic part or basic regime into the acidic regime. And thereby you have a higher release of CO2. And then the Dr. Oetker, who is well known in Germany, mainly due to this his very clever marketing, he has done one more trick in 1903. He has essentially demobilized the acidic component by adding it with the starch and drying it together with the starch first, and thereby avoiding that humidity is causing problems. You find his patent on Wikipedia, and if you read it, you find the information that per 261 kilograms of baking powder, you have 84 kilograms of sodium bicarbonate. You also find information that the formulation is still active. so that this baking powder package, which contains 15 grams of baking powder, contains 4.8 grams of sodium bicarbonate. Good. Now let's do another experiment. In this experiment, I'm mixing water with baking powder and vinegar. So I have 100 milliliters of water prepared already, and I use this. I have my 2 centiliters of vinegar, mix it, and then I add my package of baking powder, so 15 grams of baking powder, which means 4.8 grams of the sodium bicarbonate, and you can see directly bubble formation and release of CO2. Probably. Let's let it settle and continue a second. Okay. If you want to calculate this using FactSave, we may not unselect the CO2 from the gas phase. We may not unselect the HCO3 acid residue from the aqueous solution. So the only way we can do this is by working with virtual system components. So first of all, let's rescale the input amount we used earlier to 20 grams. You can do this again with a right click on the second reactant, scale all reactant amounts to a total of 20 grams. And then I again convert the acetic acid to molar amounts. I add again 0 moles of the acetic acid residue, again connected to the QA. And I add the 100 milliliters of water plus my 4.8 grams of sodium bicarbonate, which is part of the baking powder. If I then go to the species selection, I again select the QA containing species instead of the ones that do not contain QA, both in the aqueous solution and the gas phase, and then I press calculate, and this is the result I get. I see that the fugacity of the so the partial pressure of the acetic acid is now in the range of 10 to the minus 6 rather than 10 to the minus 3, which I had before. And if I smell on this mixture, I don't smell anything from the acetic acid anymore. And feel free to do this at home. It's a rather safe experiment, very impressive for the whole family. And if you look at the acetic acid in the aqueous solution, you see that most of it has dissociated, and the amount of non-dissociated acetic acid is now rather low. And we have a pH value which is slightly on the basic side. Okay, there are many further applications of virtual system components, and you will see you will see a few of them at least on the next presentation. If you go to Equilib and you click on slideshow and then advanced features, there's a chapter 15 that was added in FactSage 8.1 that has many different application examples for the use of virtual system components. It also gives references to the group at VTT, I also included a link here that you can click on to get the second reference when you use the slides that will be uploaded later on our website. And I'm very much looking forward to the next presentation by Pertti, who will show that you can use the virtual system components not only in Equilib but also in the phase diagram module. And with this, I thank you very much for the attention. If you have any question on the use of virtual system components and whether this can be done for your system as well, please feel free to contact me. Thank you.